Hello. What we're going to do is we're going to discuss something that was brought up at the end of last lesson by a student question. And the question is, was I going to cover annihilators in reference to finding a particular solution? And I mentioned that we already have, but I just didn't use the terminology. I should actually explain what I was talking about. And for a good reference is our text. Just started off the right way by using a dead marker. Page 90 to 93 of our Coddington text. Okay, 93 Coddington. And this is basically the idea in class. And this idea goes beyond second order linear differential equations with constant coefficients. But if you have something that looks like this, I'm just going to use second order for demonstration purposes. In class, I mentioned that if f of x was the kind of function stayed in its class, when differentiated, we could guess the form of the particular solution and solve for the coefficients. To obtain a particular solution, YP. That's what it said in class. Well, here, this is actually Coddington. The text makes this a bit more formal. And what they mean by making this more formal, I'm going to go ahead and get a picture of this here. But I'll let you catch your breath a second, or at least I'll catch mine. Now, being more formal is I will give you an example here. What the text says is, I'll just keep this part right here. And again, our goal is to find a particular solution. What the text notes is that if f of x is a solution to some, let's say, nth derivative plus b and minus 1, and minus first derivative plus first power plus b naught, then that process can work. But even then, it still breaks down. But now, what do we mean about this being a solution? Well, what this means is that the process works if the driving function is of some form of, let's say, wx e to the kx, where wx is a polynomial, k is a complex number, possibly 0, And W of x has degree 1 less than the multiplicity of the root k. Now here's what I mean by that. I'll take a picture here, but I want to. We'll tell you exactly what I mean by that. For example, now I'm not going to do this one because this would take forever, but let's take a look at a this sort of thing here. Let's take a look at y double prime plus let's say 6y prime plus 9y equal x e to the minus 3x. Okay. In fact, well, let's just change this a little bit. Let's say x e to the x. Now here, w sub x is just x. K is a real number 1. So what we see here is that the characteristic polynomial in question, that's not for this part, but for this to be a solution is, well, the root is, this is going to be 1, so it's going to be r minus 1 quantity squared. Because remember, when we had this as a square, perfect square, to get a second linearly independent solution, we have to multiply by x. Well, that's going to be the characteristic polynomial in question is going to be here. And on the left-hand side, the characteristic polynomial for this, the original characteristic polynomial is r squared plus 6r plus 9 equals, the characteristic equation is that. So what that's basically saying is that this thing here is going to be a solution to the differential equation you get when you multiply these two characteristic polynomials together and then re-engineer the differential equation. I don't want to do that because that's a lot of algebra. But that's basically what it's saying here. And what this basically tells you is what you have to do to find a particular solution. You're going to be looking to solutions to this, and then once you get your candidates, you're going to dump those in here just like we did. All right. So now this is going to be a little bit of a mess because we'd have to multiply and do some things. In this case, this root right here, 1, is not a root of this, because this root is r plus 3 squared. Okay. So fortunately, this isn't really a root. So what this says here is if you take this 1 and plug this into here, that should give you some information about what your YP is going to be. Now, let's make this a little easier. So this is an easy example. And I'll just show you how the algebra works for the easy example after I take this. So I'm going to modify this just to make this a little bit more doable. And I mean, the other one's doable, but no one wants to watch such a long thing. So let's go ahead and just take away this x. And let's just leave it like that. And now the characteristic polynomials just r equals 1. So looking at this from a characteristic polynomial point of view, this function annihilates the differential equation y prime minus 1 is 0. So what this says is that since 1 is not a solution to here, to figure out if we attempt yp is equal to alpha e to the x, what we can do is we can now plug in this root 1 into this equation here. Let's call this, let P of R be this differential equation. Characteristic equation of the original. So if I plug in 1 here, and that's going to be 16. So the solution will be basically 16 alpha e to the x is equal e to the x. So alpha must be 1 over 16. Now, that's pretty much what we did in class, because in class what I did is I said, okay, assume this is yp, plug this into the solution, so we get yp prime is 6 yp prime is 6 e to the 6 alpha e to the x. Yp double prime is to take this derivative again. Then if you throw this in here, we get the following alpha e to the x. I'm putting this solution into here. So this right here is 7 alpha plus 9. So this 16 alpha e to the x is equal to e to the x, which leads us to the same thing. So what was going on with this annihilator method, the key difference is that it shows you that specifically the kind of functions you can have here for driving functions for which this method works. You are still doing a calculation like we did in class. Now, I think I should probably do one more, and let's do the resonance equation. So let's take a picture here. Let's take now let's go ahead and let's do the resonance equation. We'll see how it works. And I'm going to use E. Now notice I had, so let's go ahead and let's say we have y double prime plus y equals cosine of x. That's our differential equation. Well, the way you could actually use this is you could rewrite cosine of x is 1/2 e to the ix plus e to the minus ix. Now, why is that? Well, remember, this is going to be cosine. Oh, shoot, you can't really see that, can you? So let me lower this down a little bit. Cosine of x, which I'm going to write as 1/2 of plus e to the minus ix. There we go. That's equal to that. You could see why in a second, because that's just cosine of x plus I sine of x. This replaces the sine part by the negative, and the two cancel off like that. So suppose this is our differential equation. Well, using the annihilator method, what we actually see right here is that the characteristic equation of this part is just r squared plus 1 equals 0. So r is plus or minus I. Well, what happens is that when we add to this, we actually have the characteristic equation r squared plus 1 squared equals 0. So we must induce a multiplication by x, because this is a multiplicity 2 situation. So the yp that we attempt will have multiplicity 2. And it's going to be x, to account for the multiplicity 2. Let's say a e to the ix plus b e to the minus ix. So we don't really know what we have, right? Okay. So now what we do is we differentiate. And differentiating, I get an a e to the ix plus b e to the minus ix. Then we have a x. We have a ia e to the ix minus ib e to the ix. But now let's differentiate this again. Okay. Well, here we have a ai e to the ix minus b I e to the ix. Then differentiating this, we get another copy of that. Plus x. Then we're differentiating this, and look what happens. I times I, that's minus a. And then I times minus I, that's minus a minus. What happens here, this is a minus ix. I got a little sloppy again. Minus I, minus times minus is plus. I times I is negative. Okay, so we got that. Now when we put into the differential equation, we don't really care about this. What we have is we have two copies of this. And then what we have is we have this canceling that perfectly when we add in yp. So this is what we have, and this has to equal 1/2 e to the ix plus 1/2 e to the minus ix. So what we actually have in our equations is now we know that 2ai is 1/2, and 2b and minus 2bi is also 1/2. So our basically what we have is our a is equal to 1/4. Multiplying both sides by I gives you a negative here. So if we multiply both sides by negative I. And as far as b, we multiply, but what happens is if we divide by 2, we get 1/4. Then we have a negative I here. So we multiply both sides by a positive I. We get that. There are our coefficients here. And let's see what that looks like. So, well, that looks like this. Remember, our yp was this, so. So we plug in what we know. Let's take out a 1/4 I. So what we can do is we can take out a 1/4 I. X. Well, let's just take out, let's put this in here. Of 1/4 I. We get a minus e to the ix plus e to the minus ix. But this, of course, is real. And how we know it's real is this is now x I over 4. This is going to be cosine of x minus cosine of x minus I sine of x plus cosine of x minus I sine of x. And the cosines, of course, cancel as we expect. We have a minus I, so we get an xi over 4 minus I 2 sine x. Cancel it. Yep, yep. But then minus I times I is positive 1. So we get x over 2 sine of x is our yp. Written in real form. So that's how that goes. So bottom line is that the annihilator method is really undetermined coefficients. It's just that the author does a better job of justifying what the driving functions that this method applies to, gives you why it applies to that. But the arithmetic is kind of the same. So thanks for watching.